All right. So this is, I'll have to try to do it the other way. This is Math341, lecture 22. Unfortunately, my iPad broke. Apple's being terrific in terms of fixing it. This is why you always have backup and fail-safes. This is the old emergency iPad. There was a reason why I was no longer using it to do recording of lectures, but it looks like it's going to do a good enough job for today. All right, so what I want to try to do is talk a little bit about how you would write programs to solve a couple of problems. As I have almost no voice, this is quite painful. I will be typing a little bit. If you can't understand anything, just let me know. So the first problem was the following. Given n people, what is the probability that your diploma is within one of the correct value? So if you are number 5, get either 4, 5, or 6. If there are n people, we say 1 and n are adjacent. Okay? So does everybody understand the problem? It's very similar to before. We had n diplomas, we randomly shuffled them, and the question was, what's the probability someone gets their own diploma? So now, what's the probability that your diploma's number is within one of the correct value? So what would the answer to this problem be? It would be not 3. 3 can't be the probability. You're close, so correct it. 3 over n, right? There's 3 ways it could happen, and there are n diplomas you could be assigned. So the answer is 3 over n. So that wasn't so bad. Now the next question is, what is the expected number of people to get a diploma within one of theirs? So we just said for each person, the probability your diploma is within 1 is 3 over n. Yes?
Does this loop around at the end?
It loops around at the end. That's why we're saying person 1 and n are adjacent. Yes?
Is that just 3?
Yeah, so the answer would be 3. So again, it's linearity of expectation. You know, let xi be 1 if person I gets a diploma within one of theirs and 0 else. Right? Then if x is the number of people with a diploma within 3, then x is just x1 plus ... plus xn. So, well, we converted it. Right, so it's been converted. So the expected value of x is going to just be the sum of the expected value of the xi's. So this is a really common theme. If you have a complicated problem, try to break it up into easier ones, and if possible, combine the answers. So here, it's not that bad to analyze one individual. What's the probability a specific person gets a diploma within one of theirs? It's just 3 over n. Is it possible for you to get multiple diplomas? Not in this setting, right? You cannot end up with 3 people's diplomas. So what should we assume about n?
It's finite?
We need more than just n is finite.
It must be greater than 3.
Yeah, n should be, well, it could be 3.
Well, 3 over n.
Right, if we're saying the probability is 3 over n, it's 3 over n if n is greater than or equal to 3. Right? What if n equals 2? What's the probability you get a diploma within one of yours? 100%. If n equals 1, what's the probability? All right, so if n equals 1 or 2, we can handle those directly. So we might as well assume n is at least 3. And so linearity of expectation, the expected value of x is the sum of the expected values of xi. And the expected value of xi is it's 1 with probability 3 over n, and it's 0 with probability n minus 3 over n. So that's going to just equal 3 over n. So expected value of x would just be the sum I equals 1 to n of 3 over n, which would just be 3. How would we write a program to test this? Yeah.
So we create a vector, then shuffle it, take the difference to see if they're 1 or 0 or negative 1, and then you like count the number and repeat these for a million times.
Okay, so we could do this for a huge number of times. So let's do our first programming problem. Need a name for this. 3 grad. And it will take maybe the number of iterations we do. I'll call it maybe number of iterations. And it will take a size n. Am I using bad names or? Oh, I'm still in the same line or no? Okay. All right. And then anything else we need to input? I think that's it. So Mathematica starts off with module. And then I always like to end as soon as I begin. And I'll put in a little comment, end of module. So now, what are we trying to calculate? We're trying to calculate the number of people that are correct. So we've got to be careful in terms of what we're calculating. So I'll have something called count. I'll initialize that to be 0. And I'll do for I equals 1, I less than equal to num iterations, I plus plus, begin, and then I'm going to end the I loop. So end of I loop. If you notice over here, I have another Mathematica window. It's ready to go because if I'm not sure how to code something, I can just quickly go here and test. In your main code, you'll often want to run it with small values with a lot of print statements. So if you're trying to find where the error is, put in lots of print statements to get a sense of what the output looks like. So the first thing is we're going to need a list. We might as well use the numbers 1 to n. So this is something we only need to create once, so let's just make that before we do the big I loop. List is empty, and then for j equals 1, j less than equal to n, j plus plus, list equals append to list j. Creates list of numbers. And so now we've got that created. If you're not sure if you've done this correctly, just highlight this line, plug it in here, and I'm going to just type print list. And before I run this, I should choose a value for n. Let's take 7. So list is okay because it's lowercase, but you're close. What do I have over here that I did not copy? I didn't copy the initialization. So let's try this again, but let's initialize this to be empty. Works much better now. As a rule of thumb, it's sometimes better to just overdo things and just be sure. I'll risk a potentially bad comment or joke. Shoot everybody and let God sort it out. All right, there are issues with that. Yes, you will get the bad guy, but you're going to get a lot of innocent civilians with that. Right? There are better strategies. In a situation like that, you don't kill everybody. But for those of you who play baseball, sometimes it's confusing. Sometimes base runners are going in the wrong way, and you might have 2 people on a base. If you're a fielder and there are two people on a base, one of them doesn't belong, what do?
Tag them both.
Tag them both. This is not the same as killing them. But let the umpire sort out whose base it is. You don't want to tag one person and actually it was their base, it's okay for them to be there, and then the other one runs someplace else. So as a rule of thumb, it's not bad. Let me just be extra safe. Let me just clean something up. Let me initialize it before I use it. Okay. The next thing is I'm going to need to randomly choose from the list. New list could be random sample list. And I think if I do 7, it'll give me something of size 7. And because I don't put a semicolon here, if I put a semicolon, it suppresses output. And I can always then print it by doing print new list. And as I run it a few different times, you'll see it keeps changing and get number once and only once. If I just chose a 2 there, it would just randomly choose 2 elements from the list. So if I want to just randomly sample from the list, Mathematica has something built in. So I can come in here, and then the first thing I'll probably do, but instead of 7, what do I need? N. So I will now have a random list. And now what I want to do is I want to go through and see is everybody within 1 of where you were, and if so, you increase the count by 1. So I'll have a new variable, current correct, and I'll set that initially to 0. Initialize to 0, no one is within 1 yet. And now I want to march down. What's the only thing I have to be careful about when I march? I want to make sure I'm within 1, so how do I tell if I'm within 1?
Less than or equal to 1, like it, or whatever value you're at, plus 1.
So one thing I could do is I could do for d equals 1, d less than or equal to n, d plus plus, if, and then what I'll do is I'll do new list of d, the dth entry, minus d, and I'll take the absolute value of that, and if that's less than or equal to 1, it's a success. So I would make the count, current correct equals current correct plus 1. Yes?
What about the loop, like, and?
Yeah. So hold that for just 1 second. Okay? And so that will march down, and then that will make sure that you are adding 1 if you're within 1, above, below, or if you're the same. But as was just remarked, we have this annoying wraparound.
Use mod.
So one possibility is to start to use mod, arithmetic, abstract algebra, use some more complicated functions. Yes?
I just had an idea. What if you subtract new list from list, and then you march through that difference list, and for every element that's whose absolute value is less than or equal to 1.
So we're essentially doing that here.
Okay.
Where's the only place we have to worry about this?
N and 1.
Yeah, NO1.
You could use another if statement?
Yeah. We could do an or we could do another if statement. Because we've got if n equals 1, right? Right? So if new list of 1 equals what number?
And
N, current correct equals current correct plus 1. What else would we have to do?
From this n equals 1.
Yeah. Could you code this better? Probably. Yeah. This is not that painful to do it this way. It's not going to slow things down. I would much rather code it like this. And I'll put a little comment, have to handle wraparound. And now we'll march down. And so now when we finish this, so this is going to give us a correct value. And now we add that to count. So count equals count plus current correct. And now at the end of the day, when we finish the I loop, we're going to print the average number observed that are within 1 is, and it'll just be count divided by num iterations. Yes?
Where's the end of the D?
The D loop, it's a D statement, it ends right, did I not close it? No, it's right here. So this bracket over here ends the for statement.
And it's okay to not include the ifs.
I'm sorry?
So it's okay to have the other if statements out of.
Correct.
It doesn't matter.
Correct. We have to be careful because when D equals 1, we could be looking at either n or for 2 for the solution. So if you wanted to, you could actually do this statement here just for 2 to n minus 1, and then handle 1 and n completely over here. Or we could handle part of 1 here and do the rest here. I'd rather just do part of it here. The other thing is, if n is a small number like 1 or 2, there may be an issue with this. But as long as n is large, we're fine. We've got to be careful that we don't ever double count. And so we're not double counting here. And then what we've done is, if we have a shuffling that has 5 people that are within 1, we've increased count by 5. If we have a shuffling that has only 2 people that are correct, we increase count by 2. And so we have to divide by the number of iterations we do, and that will be the average value. I'm putting in the 1.00 so it returns a decimal. Right. Before you run any programs, you should save them. So let's go to, we're saving downloads for now. All right, so this is Math341 diploma problems. Why do you save a program before you run it?
If it crashes.
If it crashes. So I am extremely paranoid. When I write programs to save things to files, I actually save it to files twice. Why do you save it to a file twice? If you have the file open and you're saving it to the file and the system crashes, you could lose the file and lose everything. That's why you save it to a file and then you immediately copy that file. That way you always have a copy of your data. There's been a couple of times when stuff like this has really saved me. That you can have crashes at very bad times. And by having 2 copies, yes, it's a little bit slower. But if something goes wrong, you are protected. A few years ago, a computer science major who had taken classes with me confided she had never seen Star Wars and she was interested in computer graphics. I told her she cannot graduate from Williams without seeing Star Wars. You will just be at a disadvantage. So we were showing Star Wars and the DVD stopped playing halfway through. I reached in and I took out the backup DVD. If necessary, I had it on VHS. If there is something that is critical to what you are doing, you have a backup. I have been at a huge number of events where there are no backups when there could be. People are giving talks. Oh, the internet's down. My slides are only online. I don't have my slides on me. Always have backups on you. All right, so do we think that this should work? So we can try 3 grad. Let's do 100 iterations with 10 people. The average number is 2.8. All right, so we're going to just make this a little bit larger. So let's do 10,000. And then if you put the word timing around it, be a little bit better. I'm a little concerned that it's always below 3. Now I feel a little bit better. It should be on both sides. And the timing tells you how long it's taking to run. It's taking about a quarter of a second. So how long do you think it should take to do 100,000?
2.5.
It should take about 2.5 seconds, because this is a problem that I'm just running more iterations. Now the harder one is if I go from 10 to 100, how long will that take? Any thoughts?
Could you scroll down a little bit?
I'm sorry? Scroll up or scroll down?
Like, towards the bottom. Yeah.
There's nothing there.
Okay. Well, it's up.
Oh, the time. Oh, I'm sorry. It was 2.4 seconds before. Now I've increased from 10 people to 100 people. I would have guessed around 25, 24 seconds. That you might. I'm just going through the list. If I decrease this by 10, it should be about 1.8 seconds. 1.85. So if I went from 100 to 100 to 1,000, how long do you think that should be? That should be about 18 seconds. Yes?
Why is the average number 3 at 100?
Oh, interesting question. Oh wait, that's what we proved.
No, yeah, it doesn't matter then.
Right.
Oh yeah.
Right.
I was thinking theorem. Probability, not fill.
Right. And so we now get 18.6. So we see that it really is scaling the way we would expect. The other thing is, if you're not sure if things are working, you can put some statements in this. Watch these kind of statements. If n equals, oh no, we're not doing, I is the loop variable. If I equals 1, print list space new list. And I'll close off the if statement. So now it's only going to do this the first time. So I'll make my list only 10 people. And so now it prints my list and my sorted list. What else is something you might want to print?
The number of matches.
Yeah, so match might be a much better word than count. So let's do if I equals 1, print number of matches is, and now we'll just do current correct. So it says there are 2 matches. 5 doesn't work, 7 doesn't work, 8 doesn't work, 10 doesn't work, 6 works, so that's 1. 3 doesn't work, 1 doesn't work, 9 and 8 work, 4. So this showed us there were 2 matches. One of the things we could do is, instead of having the print statements there, we could actually put all the print statements together. It's sometimes nice to go like this.
What's the double and sign?
So the double and sign is the binary connective. It means just and. So if I do 2 vertical lines, that's or. So if I equals 1 and print check equals 1, do the following. So what I'm going to do is I'm going to add another quantity here. I'll add print check. And so now when I run it, if I put in a 1 here, it's going to print those statements. Whoa, should have printed those statements.
Should that be equals 1? Print check equals?
Yes, it should be equals 1. Thank you. Good catch. So now, when I put a 1 here, it prints out all of my print checks. If I put in a 0 or anything else, it doesn't. You know what's wonderful about this? Let's say you have certain parts of your code that you are concerned about. You can have different levels of prints. If the print is 9, print out everything. If it's 7, print out only things up to here. So you can actually code how much you want it to be displaying for you. So little tricks like this will make it a lot easier for you to debug. If you're not sure about some of the code, you just pop it into the other side and just test it there. Okay, so any questions about this? So we should have been having it do a huge number. So the more points you have, the more accuracy you should expect. So with 100,000, 2.99995, I'm pretty happy with that answer. You expect convergence often to be like at the 1 over square root level. So if I go up by a factor of 100, I would expect to gain one more decimal digit. Just to give you some idea of how much work do you need to get for these accuracies. All right, any questions about this code? All right, so the next problem was now consider a success if diploma is the same parity as yours. So even, or odd, not even, odd, or odd, even. Now, what is the expected number of successes? All right, so does everyone understand the problem? So if your diploma is 5, if you get a 1, a 3, a 5, a 7, a 9, an 11, you consider that a success. So we can solve this both theoretically and we can solve it with computer simulations. Which would you rather do first, the computer code to build intuition or the theory? Theory? Code? Yes?
Will we be concerned if we have like 5, so like 3 odd, 2 even, rather than like 3 odd, 3 even? Do we need to like subdivide those cases?
So that might come into play in terms of what the probabilities are. Is that if you have an odd number, it may be different than if you have an even number. So the parity of the number of people could matter. So this is a real question. Should you do theory then experiment, or experiment and then theory? If you do the experiment first, you might be tempted to view certain theoretical calculations as correct because they're matching your experiment. So there's a danger sometimes where if you know the answer, it's going to lead you to arguing to get that. I will send you one of my favorite stories by essays by Isaac Asimov on the planet that wasn't. The 1800s were a little bit different than the 21st century. The rock stars were sometimes people of science. And one of the greatest rock stars in Europe was the person who predicted not just the existence, but the location of Neptune. This was because there were some issues with the orbit of Uranus. And they said, well, since Newton's law of gravity is working so well at every other place, if there were a planet beyond the orbit of Uranus, it would really only affect Uranus. The effects would be much smaller for all the other planets. And 2 different people predicted where it should be. One of them had greater success in convincing people with telescopes to look there, and that's the person who's now celebrated. A little bit later, people turned to Mercury, and the orbit of Mercury was not quite right. This is if all you have is a hammer. Given that he successfully predicted Neptune, he said there must be a planet between the Sun and Mercury. And it's small, and that's why it's only really affecting Mercury. Why did nobody ever see this planet? I'll accept 2 answers.
Doesn't exist.
Doesn't exist is one answer. Why else? Why would no one have seen the planet between the Sun and Mercury?
It's too small.
Not quite too small, but close.
Sun is too bright.
The Sun is too bright. You're basically looking right at the Sun for a planet. So you could only see this during certain types of eclipses. And so when one of these eclipses came, they said, point your telescopes here and you will see the planet. And what happened when people went to do the experiments?
No planet.
Most saw no planets. And a couple of people, yes, that's the planet. I'm the one who verified the theory. I saw the planet. This is the danger when you know the result or when you think you know what the result is. It will influence your behavior. To some extent, this lesson is more important than all the integrations we've been doing all semester, is how to be impartial and not be misled. So one of the things we could do to try to prove this theoretically is we could try to do it by recursion. If n equals 1, probability is 1. If n equals 2, probability is, or I guess, sorry, it's not probability, expected number of successes. So if n equals 2, the expected number of successes is, well, we could have either 1, 2, or we could have 2, 1. With 1, 2, both are correct, and you have 2 successes. With 2, 1,
It's 1, right?
so it's 1.
It's 1/2 times 2.
So, which is equal to 2 times 1/2 plus 0 times 1/2. If n equals 3, we have 1, 2, 3. We have 1, 3, 2. I guess I'll do it with commas. Maybe not. So we can start going through all the different cases. Let's do it like this. All right, 1, 2, 3, 1, 3, 2. Then we could do 2, 1, 3, 2, 3, 1. And then we could do 3, 1, 2. We could do 3, 2, 1. So in this one, how many successes do we have?
3.
And they all have probability of 1/6. So we can divide by that. In this one, how many successes do we have? 1 success. Just the 1. In this, how many successes? 1 success. In this, how many successes? 1 success. In this, how many successes? 3 is a success,
Oh,
right? And in the last one, how many successes? 3. Everybody's a success. 3, 4, 5, 6, 7, 10. So it's 10/6 or 5/3. So the pattern is a little bit more interesting now. So we could try to develop a formula. Imagine we have n people. And it might be easier to look at evens or odds. So let's look at an even number first. What's the probability the first person is matched with the correct parity?
1/2.
1/2. So half the time, we're going to get 1 from the first person being matched correctly. And then the expected number would be just a 2n minus 1. Or half the time, we don't have somebody matched correctly. So if they're not matched correctly, then they're matched with somebody else who's wrong. Right? So if I'm an odd person, I'm matched with an even, and then there's an even later down who's matched with an odd, we can just remove the 2 of us. And now how many people are left? 2n minus 2. So something like that might be the formula for the even case. And then I'll leave the odd case for you as an exercise. So if you had trouble with the exam, here's a great practice problem to do. Feel free to come to my office and show me, hey, I was able to do this. And then we would have this recursion formula. And so you might be able to come up with a closed form solution, but even if not, well, as long as I know the earlier values, I can calculate the next values very easily. I can write a code to just march down the line. All right, so now let's write a program to do this. In the interest of time, I'm going to just cut and paste. So let's just start off, and we'll call this parity check, parity grad. I'll have print check numbered as before, count list as before. What's the only thing that really changes?
The checking mechanism?
Yeah, the checking mechanism. So in fact, it's a lot easier. I can get rid of these cases of n and 1. I don't have to handle the wraparound. So now I want to just recall how Mathematica does mod. If it's 10 o'clock now, what time is it in 5 hours? 3. So everybody agrees that 15 mod 12 is 3. So I just want to make sure I put things in the right order. So you put the number first and the modulus second. So this will look at the remainder of 15 when you divide by 12. If instead of doing 12, if I do 2, it'll give me a 1 if it's odd. Oops. And if it's even, it will give me a 0. Okay? So when I come here now, I want to march down and I want to just check and see if they're the same parity. So there's a lot of ways to do this. I could just go if mod, what's it called? New list D mod 2 equals mod D mod 2.
Should that be equals equals?
Yes, it should be equals equals, thank you. So if they're the same parity, increase by 1. Is there anything else we need to do?
Does that account for odd numbers as well?
Yeah, we just march down.
Okay.
So we now have our parity program to check. What's the first n we should run it on?
10 or something.
No,
1.
1. We'll do 100 times with one person. Why should we run it 100 times with one person?
100 will be 12.
I'm sorry?
So we should always just get the same answer.
We should always just get the same answer, and it should be an answer we know. This is a sanity check.
Should be 1.
If it's not 1, boy, are we in trouble. Oh, I didn't compile the line. Right. So I must have misspelled it. Oh, it's parity grad? It's parity grad. All right. The average number observed that are within, oh, I have the wrong language. The average number of same parity. Okay. All right. So building on a success with 1, we should now try 2. All right, we got a value of 0.9. Is that good? Yeah. So now let's go up to 10,000. And we got 0.99. That's not bad. What should we try next? 3. What's the answer with 3? 5/3, which is
1.67.
1.67. So how confident are you that this is going to be 1.67?
4 decimal places.
All right, so you think we'll at least be close. 1.668. All right, I'm feeling much better now about the theory. Right? And this was really fast. So we can add a few more zeros. This should take about 9 seconds. 9 seconds is not a huge amount of time to wait.
What's a strategy for making code more efficient so it doesn't take a really long time?
So one question is to see, are there steps you can save? And I don't think there's really that many steps we can save. Now, one of the things we could do, of course, is what is our list? It's the numbers 1 to n. Do we need the numbers 1 to n?
There should be 1 to 100 or something. Right?
What should we have as our numbers? Not 1 to n, but when I give you a number like 5, what do I care about 5? If it's even, so what should my list be composed of? Zeros and ones. So don't do a big list like this. We could do mod j by 2.
Would that make it faster?
I mean, you will work with slightly smaller numbers. I don't think it's going to make a huge difference.
You're adding mod, but that might take longer.
But we only use, well, here's the thing. But now here's the advantage. We are only using the mods. So
you can take out the mods.
over here now, we could just say if they are equal. right? So now instead of using the mod argument, we can now just say if new list D equals mod D2. So we save a mod, right? So before it took 9.29 seconds. We'll see if there's any real savings here.
How are you saving anything? We're just-
Look at that. There was a savings. Because before, we had to take the mod of all the new list elements. Is it even or odd? Well, we can, instead of doing that every single time, just do that when you create the list. Make the list all zeros and ones. 0 if it's in an even location, 1 if it's in an odd location.
Does it give you the same answer?
We got 1.6674, yes.
Okay.
So it's basically giving us the same answer. It's not a huge savings. So much of the programming time is just going through the list. But the mod did take time. This is almost an 11% savings. That's not insignificant. So your question of, can you make the code more efficient? Almost surely. Sometimes it's not worth it. Now, if we want to go up to, say, 10 people, let me remove cap locks. And then I will make this a little bit smaller. So with 10 people, we've got about 5. And you can start, and you can do some of these cases by brute force. If we actually did enough to get the odds, you could then calculate exactly what 10 is. So if you feel that you are having trouble showing me what you really know in this class based on the exams, here's a problem for you to do. Build up the theory, calculate what it should be with 10 people, run the code, and show me that it matches your theory. Ideally, I would like you not to run the code I have here. I'd like you to write your own code. Right. Any questions on this? But it was really nice to see how we're able to speed up the code. Theoretically, does it matter? No. But if you're going to do something many, many times, if you can get away with doing it just once, that's much better. Think back to all the stuff we did with decks of cards, right? We would have the kings be 1s and the queens be 10s. And we could do a lot of tricks like that. You can do it the long way, and it sometimes means more involved coding. But if you can think of small things like this, and again, in what we're doing here, it doesn't really matter. My brother has worked on, I probably shouldn't say things with the camera rolling, but there are times when those small savings do make a difference, and you don't have that long. Have you ever watched a police show where they're trying to trace a call? How many times have you heard the officer ask the person, could you stay on the phone just a little bit longer? We've almost got your location. It seems like the bad guys always know exactly how long it's going to take, and oftentimes you see them, you're looking at their watch and having fun. Now hang up. I think they have a scene like that in the movie Sneakers, great movie. If you can do things a little bit faster, that's a great application there. All right, so again, this is one of the things I wanted to do by moving some of the class online. So by having you do 24 minutes at home, that freed up today to talk about, let's do another problem, let's do some theory in detail, and let's do some coding in detail. And now go home, try to get it work, and if it's not working, try to debug it, and then let me know. All right.